Welcome to this comprehensive guide on JPEG compression. JPEG stands for Joint Photographic Experts Group, and it's one of the most widely used image compression formats in the world. Let's understand how this elegant compression algorithm works, step by step. JPEG compression consists of 7 main stages that work together to reduce file size while maintaining acceptable visual quality. Each stage exploits specific properties of images and human vision to achieve compression. Let's dive into each one. Stage 1. Color space conversion. Digital images are typically stored in RGB format, with red, green, and blue channels. However, JPEG converts RGB to YCbCr color space. Why? Because the human visual system is more sensitive to brightness than to color. In YCbCr, Y represents luminance or brightness, while C flat and crossing represent the blue and red color differences. The conversion formula uses these coefficients. Y equals 0.299 times R, plus 0.587 times G, plus 0.114 times B. Similarly, C flat and crossing are calculated with their respective coefficients. This separation allows us to compress color information more aggressively than brightness. By separating luminance from chrominance, we can preserve detail where our eyes are most sensitive. Stage 2. Chroma Subsampling. This exploits the fact that human vision is less sensitive to color detail than brightness detail. The most common scheme is 4:2:0 subsampling. In this scheme, the Y channel stays at full resolution, but the C flat and crossing channels are reduced to half resolution in both dimensions, keeping only 1/4 of the color data. This simple step achieves a 50% reduction in data before any other compression, and for most photographic images, it's virtually imperceptible. This is one of the most elegant tricks in JPEG's arsenal. Stage 3. Block splitting. Each color channel is divided into 8x8 pixel blocks. Why 8x8? It's the sweet spot between compression efficiency and quality. Smaller blocks give less compression. Larger blocks create more artifacts. Before applying the DCT transform, we shift pixel values from the range 0 to 255, down to -128 to +127. This centers the data around 0, which improves the mathematical properties of the next step. Stage 4. The Discrete Cosine transform, or DCT. This is the mathematical heart of JPEG compression. The DCT converts our 8x8 block from the spatial domain, where we think about pixels, to the frequency domain, where we think about patterns. The two-dimensional DCT formula looks complex, but it's essentially decomposing the image block into a sum of cosine functions with different frequencies. The magic of DCT is energy compaction. After transformation, most of the important information concentrates in just a few low-frequency coefficients in the top left corner. The top left coefficient is called the DC coefficient and represents the average brightness of the block. The rest are AC coefficients representing different frequencies. High frequencies in the bottom right often become very small or zero, which is perfect for compression. Stage 5. Quantization. This is where JPEG becomes lossy. It's also where most of the compression happens. Each DCT coefficient is divided by a corresponding value from a quantization table, then rounded to the nearest integer. The quantization table has small values for low frequencies, which we want to preserve, and large values for high frequencies, which we can afford to lose. Notice how large coefficients become much smaller, and small coefficients often become zero. This creates lots of zeros, especially in high frequencies. The quality factor you choose when saving a JPEG controls how aggressive this quantization is. Higher quality means less quantization and larger files. Stage 6. Zigzag Scanning. After quantization, we need to convert our 8x8 matrix into a one-dimensional sequence. But we don't just read it row by row. Instead, we use a clever zigzag pattern that reads low frequencies first and high frequencies last. This pattern groups all the zeros together at the end of the sequence, which is perfect for the next step. Entropy encoding. See how all those zeros cluster at the end? That's exactly what we want. Stage 7. Entropy encoding. This is the final compression step, and it's lossless. JPEG uses two clever techniques here: run length encoding for the long sequences of zeros, and Huffman coding for efficient binary representation. Run length encoding represents repeated zeros efficiently. Instead of storing 0, 0, 0, 0, we store 4 zeros. Huffman coding then assigns shorter binary codes to frequently occurring values and longer codes to rare values, like Morse code for data. Together, these techniques squeeze out every last bit of redundancy, creating the final compressed JPEG file. And that's how JPEG compression works. Let's recap the 7 stages. First, RGB to YCbCr conversion separates brightness from color. Second, Chroma Subsampling reduces color resolution. Third, we split into 8x8 blocks. Fourth, DCT transforms to frequency domain. Fifth, quantization discards imperceptible information. Sixth, zigzag scanning orders coefficients. Seventh, entropy encoding compresses the final data. Each stage cleverly exploits properties of images and human perception to achieve compression ratios of 10:1 or even higher, while maintaining good visual quality. JPEG has been the gold standard for photo compression for over 30 years. And now you understand why. It's a beautiful blend of mathematics, psychology, and engineering. Thank you for watching this guide on JPEG compression. I hope you now appreciate the elegance behind every JPEG image you see.